Well, we still have folks joining right now, but I'll go ahead and get started slowly with some of the logistics reminders while we have participants getting on the webinar. Welcome, this is Paige Johnson with American Wind Wildlife Institute, and this is the NWCC webinar on new research on smart curtailment for bats at wind energy facilities, supported by the U.S. Department of Energy. So before we get started with the presentations today, I'll go through a few of these quick logistics notes. For sound, you should be able to hear us through your computer. There is a dial-in number that you are welcome to try. We've been experiencing some difficulties with this due to nationwide increase in usage. So if you're having trouble, you can try dialing in a few times. Sometimes that works. But if you're not able to get through easily, then you can always listen to us over your computer speakers. And if you are on the phone, please mute your line so that we don't get any background noise. If you're having any technical trouble with the webinar, you are welcome to email us at support@kernswest.com. That email address is in your notes box on your screen. You can also enter your logistics questions in the Q&A box, and we'll have our tech support help you out. So for the Q&A for the presentations, what we're going to do today is have a few minutes of Q&A after each presentation. We have 4 presentations. And if you have a question, you can type it into the Q&A box at any time during the presentations. And at the end of the presentation, I will read the questions out loud for the presenter to respond to. You'll only be able to see the questions that you submitted, not ones that others submitted, so we will read them out loud so everyone can know what the questions are. If we have extra time at the end of the webinar and we've had to skip some questions for time purposes to make sure we get through all the presentations, we will circle back and try and get your questions answered. But if there are outstanding questions at the end of the webinar that we didn't get to, we will try to answer those by email and have the presenters address your questions by email. And then lastly, a reminder that we are recording today's webinar, and the recording and the presentation slides will be posted to the NWCC website within a few days. So once again, thank you for joining us. And to start, I am going to turn it over to Jocelyn to give an introduction. Jocelyn Brown-Saracino is the Program Manager for Market Acceleration and Deployment at DOE's Wind Energy Technologies Office, and she's going to introduce the projects today. So whenever you're ready, Jocelyn, take it away.
Okay, great. Thanks so much, Paige, and thanks in advance to all of the speakers for presenting today, and to all of our attendees for joining us. All of the work that you're going to be hearing about today is new research supported at least in part by the U.S. Department of Energy's wind program. So as a bit of context framing before we launch into the individual talks about the research projects underway, I'm going to provide just a little bit of context about the program out of which these projects were supported, and provide a little bit of background on our strategic objectives with regards to wind and wildlife work, as well as wind research around reducing impacts on bats more specifically. So the U.S. Department of Energy's wind program, or Wind Energy Technologies Office, works to support research that both helps reduce the cost of land-based wind, offshore wind, and distributed wind, but also works to address challenges around environmental impacts and other siting-related challenges for wind energy development, and then also to ensure that wind energy is a good player on our electrical grid. And we support research. We're primarily a funding entity, and we do that through a variety of different mechanisms, either through support of one of the DOE networks of national labs, through competitive solicitations, or through collaboration with federal partners. And for about just over the last 25 years, the wind program within the Department of Energy has been supporting environmental research to help us better understand and minimize the impacts of wind energy on wildlife. We have a strategy that's three-pronged in nature. We support the collection of data and experimentation to really understand species exposure and the factors that drive risk. We support the advancement of both monitoring solutions and mitigation or minimization solutions. And then finally, we invest in a body of work to really make sure that research going on around the world is synthesized and made public and is widely disseminated in order to help reduce redundancy of research, make sense of potentially disparate studies, and really to make sure that we're doing what we can to share information so that we can expedite the development of solutions. And specifically with regards to wind energy and bats, we've been supporting research in this space for about 15 years, and our strategy with regards to bats and wind energy is really to support work that help us really understand what are the factors that are driving risk to bats at turbines, then also to help develop and assess the potential efficacy of impact minimization measures. And then in the future, if as needed, we may support the development of an assessment of potential compensatory mitigation options. And DOE and our national labs have been supportive of the Bats and Wind Energy Cooperative since its inception in 2003. And the BWEC research funded through the BWEC has been pivotal in developing some of the most promising solutions, kind of the early stages of some of the most promising solutions to reducing impacts of wind turbines on bats, including early research around exploring the possibility of cut-in speed adjustments to reduce mortality of bats on turbines, and some early work on the development of ultrasonic acoustic deterrents. And based on the research that was done, early research done both by the BWEC, but also by a number of other folks, including a number of the speakers you're going to hear about today, DOE felt like there was promise in exploring potential solutions to help refine some of the curtailment methodologies, to move from having, supporting some of the research already underway and advancing it, from moving from kind of a concept of blanket cut-in speed adjustments to really trying to refine curtailment options so that we're curtailing only at periods of greatest risk for bats. And through this, the aim is both to help either improve or maintain protection for bats while reducing the amount of energy loss that's experienced by the wind farm through curtailing operations to help protect bats. And we did this through a solicitation that was issued by the Department of Energy in 2018. The solicitation had three different topic areas. Two focused on solutions to minimize impacts of wind energy on bats, including the work around advancing smart curtailment strategies that you're going to be hearing about today, as well as work to advance bat deterrent technologies. And just a note that if you have interest in learning about the bat deterrent technologies and you did not participate in the earlier webinar that we had on these projects last week, just a note that that occurred, and a recording of that webinar will be able to be found on the NWCC webpage as well as the TEFIS webpage in the future. And then similarly, we had a third topic area under this solicitation focused on development and validation of offshore wind monitoring and mitigation technologies. And earlier this winter, we held a webinar on this topic. So if you have interest and you missed that, those recordings are already available on the NWCC and TEFIS websites. But the focus of this webinar today will be highlighting the work that is ongoing and will occur over the next couple years really working to refine and validate solutions for refining curtailment efforts, for making curtailment smarter. You're going to be hearing about work underway by 4 different entities. You're going to be hearing from Stantec and AWWI on solutions to develop models to try to predict and then curtail wind at periods when bats may be at greatest risk. And you're going to be hearing from Natural Power and EPRI about approaches that use bat acoustic detection in real time to inform curtailment decisions. And then I'll just one last note before I close, that all of the work supported by DOE when it is published.
The leader has muted your line. To unmute your line, press #6.
Paige, can you still hear me?
Are you still there, Jocelyn?
I am. I just got a note that I was muted.
Oh, I was sorry about that. I was muting the non-presenter lines, but anyone who's called in as a presenter should still be fine.
Okay, great. So just one quick last note from me. All of the final reports from work that's funded by the Department of Energy's wind program with respect to environmental research is hosted on the TEPIS website, as is research studies on both offshore and land-based wind from around the world, so it's not exclusive to DOE resources, as well as recordings of past webinars, information on upcoming events, etc. So if you have interest in seeing the final results from these projects when they conclude, or from previous work funded by DOE's wind program with respect to environmental research, I'd encourage folks to check out the TEPIS website. And with that, just want to thank Paige and AWWI again for organizing, thank the speakers for your willingness to present today, and to the group of folks who are logged in now for your interest and attention. And if you have interest in learning more about the wind program at DOE's environmental program more generally, the web address can be found on this slide here. And thanks, Paige. I'll pass it back to you.
Great, thanks, Jocelyn, and sorry for that little technical disruption. Thank you so much for that intro, and now we will turn it over to our first set of speakers. We have Trevor Peterson and Adam Rusk from Stantec. So Trevor, whenever you see your slides up there, you can go ahead and start with your presentation. Let's see, did we lose Trevor? I don't think we can hear you. All right, everyone, sorry for the logistical issue. Let me see if I can unmute. Trevor, if you can hear us, to not be included in the blanket mute, you need to call in as a leader with the leader pin that we provided you. So if you're able to hear, maybe try calling back in with the leader code. All right, thanks everyone for your patience. Give us just a second.
Hi, can you hear me now?
Yes, thanks, Trevor. Sorry.
Okay. Sorry about that, everybody.
Very sorry about that disruption.
I appreciate AWWI for hosting this webinar. and certainly to the Department of Energy for supporting these projects, and to all of you who are joining from wherever you may be. So I'll kick off things today with an overview of smart curtailment research that Stantec has been involved with, actually going back as far as 2011, and which will lay the foundation for what we're proposing to do with our DOE funded research over the next 2 years. So the reason we're here, obviously, is to discuss the issue of bat fatality at wind farms, which has vexed not only the wind industry but regulatory agencies since its discovery in the mid-2000s. And more recently, concerns over potential cumulative impacts to hoary bats have renewed discussions over the need to reduce fatality rates across the industry as a whole. Bats are at risk only when turbines are operating, and this is ultimately why curtailment works. So curtailment is simply feathering turbine blades to prevent turbine rotation during a certain combination of parameters. And most curtailment plans use simply wind speed alone, although the threshold cut-in speeds are typically determined by some combination of industry or regulatory precedent rather than site-specific information on risk. And I'm referring to these strategies as blanket curtailment. Our definitions may not align completely yet, but in my opinion, what defines blanket strategies is not necessarily the parameters they use, but the fact that they do not take into account site-specific data on risk. So blanket curtailment plans might include a temperature threshold as well as cut-in speed, but they tend to use the same cut-in speed triggers over broad seasons. And by contrast, I define smart curtailment as strategies that focus turbine shutdowns on periods with high risk, as defined by site-specific data. So smart curtailment programs typically include multiple parameters or multiple trigger points as opposed to a single cut-in speed. But the defining feature is that they are informed by site-specific information on risk. And I think this is a useful definition because it's flexible in terms of what parameters or trigger points are used. It really gets at the heart of the information behind the curtailment strategy rather than how it's accomplished. So what Stantec has been doing is use acoustic detectors to measure bat activity at nacelle height, and then use the empirical distribution of bat activity to indicate risk. So it's not necessarily a model, but it's using the distribution of activity itself to calculate the amount of exposure, the amount of bat activity that's exposed to turbine operation under different strategies. Simply put, we design curtailment programs to prevent turbine operation during conditions when most bat activity occurs. So importantly, we differentiate between bat activity that occurs when turbines are on, so using a threshold of 1 RPM is operational, versus activity that's occurring when the turbine is off. So which parameters are ultimately used to trigger curtailment can be determined best once you have site-specific information linking bat activity and variables like temperature and wind speed. So accordingly, our approach to smart curtailment is more a framework to quantify risk using acoustics rather than a specific technology or curtailment system. So we first began thinking about using acoustics to design curtailment programs back in 2012 when working at the Laurel Mountain Wind Project in West Virginia. We conducted simultaneous acoustic monitoring at nacelle height and standardized carcass monitoring there from 2012 through 2015, and later on at the nearby New Creek Wind Project in 2017 and 2018. So in each year we had anywhere from 6 to 10 bat detectors installed at turbine nacelles and conducted simultaneous standardized fatality monitoring. So together these projects generated an unprecedented set of acoustic and fatality data we could use to evaluate the relationship between bat activity and fatality risk. So the first part of our DOE research project was to go back and combine data from these two sites and test some of the assumptions underlying our activity-based curtailment framework. And that circle shows an example of where the detectors are placed, near the back end of the turbine. So a single bat detector obviously can't record activity within the entire rotor swept area, but what it does provide is a representative sample of the conditions during which bats are active. I like to display these with a heat map. So this is basically a picture of all the bat passes recorded at both projects over multiple years and their distribution relative to wind speed on the horizontal axis and temperature on the y-axis. What you see is that most bat activity occurs during warm temperatures and relatively low wind speeds. And this is basically has been shown time and again with fatality data, but at a much coarser scale. The nice thing with acoustics is that you can actually calculate the amount of the proportion of bat passes below particular cut-in speeds, whether they're associated with a curtailment plan that was actually implemented or one that's being considered or evaluating. So most of you are probably aware that acoustic data and fatality have not been shown to be highly correlated or consistently correlated based on previous studies, and especially those comparing pre-construction acoustics and fatality data. In fact, this is also the case when you compare overall bat activity at nacelle height with fatality rates, which is shown in this graph, where each dot represents an empirical fatality estimate on the vertical axis and the total amount of bat activity measured at corresponding turbines on the y-axis. Blue dots represent Laurel Mountain and red represents New Creek. So what you see is there's essentially zero relationship. It's a flat line, no R squared. So there's really, the amount of bat activity here doesn't play into fatality rates. However, if you take away the bat activity that occurs when turbines are off, which is it turns out is a lot of the activity measured in these systems, the picture changes quite dramatically. And when you look only at the subset of exposed bat activity, so again, those passes occurring when RPM is greater than 1, you suddenly have a much stronger relationship. In this case, an R squared of 0.8 and a significant relationship. We tested this relationship on different scales, including the probability of finding a carcass during an individual turbine search on the left and the total number of carcasses, raw carcass counts found per turbine on the right. And in both cases, exposed bat activity explained a significant amount of variation in the probability of carcass detection, or the number of carcasses detected. So the first major point of our analysis from Laurel Mountain and New Creek is that exposed bat activity has a significant positive association with fatality on multiple scales, and I think is therefore a reliable quantitative metric of risk. So I'll move through this relatively quickly, but this essentially shows that bat activity followed consistent seasonal patterns in terms of species composition and distribution versus temperature and wind speed. So the upper plot is pie charts showing the monthly number of bat passes by species at Laurel Mountain and New Creek, and you can see visually that they're very similar. Silver-haired bats were accounted for much more of the activity in September, and most bat activity occurred between July and September. Anybody who's conducted a fatality study will know that these patterns are very similar to the overall patterns in carcass detection. But we really wanted to know how predictable exposure of bat activity is on a finer scale. So what we did was take a multi-year data set and calculate for every turbine the number of bat passes and the proportion of activity exposed to turbine operation at every turbine according to each of 8 different curtailment programs. We then went back to the data from the previous year at the same turbine and predicted how much activity we think would have been exposed with that same curtailment strategy, and then combined these. And what you see here is a scatter plot as simply a linear regression of the predicted exposure on the horizontal axis and measured exposure on the vertical, keeping in mind that predicted data and measured data were from different years. So even when using a log-log scale, which accentuates differences at the low end of the scale, the correlation was over 80%. So what this means is that the amount of exposed bat activity can be predicted accurately even with data from a single turbine. And these predictions become even more accurate when you combine the data among turbines. So exposed activity may be a meaningful indicator of risk and also is predictable. So how do we use that to design and evaluate curtailment? Well, firstly, you can compare curtailment alternatives very well with acoustic data. What these plots show is the distribution of the predicted percent of reduction in the percent of bat activity exposed to turbine operation, with each turbine data being considered independent, associated with curtailment treatments ranging from 3 to 6.9 meter per second. So these are half meter per second scales. And just as an initial visual inspection, you can tell that it's relatively easy to discern these strategies in terms of the amount of reduction in acoustic exposure. The same is certainly not true for fatality studies, which have been unable to resolve differences between strategies with cut-in speeds differing by as much as 1.5 to 2 meters per second, so 3 to even 4 of these differences. So at the bottom line, acoustic data is simply far more, you get a far better sample size of bat passes per turbine than you do carcasses, particularly in the presence of curtailment. Curtailment does not appear to affect the number of bat calls recorded, and so you come up with relatively equivalent sample sizes regardless of the curtailment strategies. More importantly, however, you can simulate a wide range of curtailment strategies using acoustic data. And what we did as part of this exercise was take the parameters from 15 blanket curtailment strategies recommended by agencies in North America, and we used the data from each project to simulate predicted energy loss and reduction in exposed bat activity according to each curtailment strategy. So every dot here represents a prediction of energy loss indicated in the horizontal axis and reduction in risk indicated in the vertical. And these are based on aggregated data from all turbines in all years at each site. You can see that the predictions are remarkably similar between Laurel and New Creek, even especially for risk reduction, even though these data came from different projects in different years. Yet the plans themselves differ widely in terms of predicted cost and effectiveness. So in this case, I wanted to highlight examples of plans that have equivalent predicted exposure, reduction exposure, so the vertical scale again, with substantially different energy loss. And what we do, our goal is to really design alternatives, curtailment alternatives that offer equivalent or greater reduction in exposure for the least amount of energy loss. So looking in at these subsets, what we did in this case was adjust the parameters. In this case, all we used was temperature and wind speed adjusted on a monthly basis. And we were able to design strategic alternatives that achieved equal or greater reductions with substantially less energy loss. In fact, simply by changing temperature and wind speed every month, we were able to design alternatives that were equal or better than all of the curtailment strategies we simulated, with an average of 40% less energy loss. So smart curtailment does not necessarily need to be complicated to be effective. It takes advantage of the known patterns in risk, and the complexity of the plan is essentially dictated by the targeted level of risk reduction. So our DOE-funded research builds on the results from New Creek and Laurel Mountain. And what we plan to do is record acoustic bat data at 15 turbines at each of up to 3 wind farms. And each site, subsets of turbines will be feathered below normal cut-in speed and curtailed according to a blanket curtailment strategy. Simultaneous fatality monitoring will generate an empirical fatality estimate for each treatment. So just like we did at Laurel and New Creek, we'll use the first year of data from each site to measure reduction in exposed activity for each curtailment strategy. And we'll try to design a strategic alternative that achieves the same level of reduction for less energy loss. During the second year, we'll implement both of these strategies, the blanket strategy and the smart curtailment alternative, and we'll repeat acoustic and fatality monitoring to measure the exposure reduction and directly test the accuracy of our predictions. We'll then combine both years of data and compare exposed activity and fatality at the same 3 scales used for New Creek and Laurel. And this will be the real empirical test of the assumptions underlying our smart curtailment strategy. So we'll use fatality data to demonstrate that exposed bat activity correlates with risk, but we'll then rely on acoustic exposure as the primary metric to design and compare strategies. We hope to demonstrate that use of acoustic at nacelles could change how we think about curtailment towards a framework where we define strategies in terms of target reductions and fatality risks rather than the parameters themselves. The alternative, where we are now, is essentially agencies and wind farms negotiate over cut-in speeds as opposed to the goal of reducing risk by a certain margin. And I'll wrap up with an analogy. blanket curtailment, in my mind, is sort of like trying to determine an appropriate speed limit for a road without any information on traffic volume, pedestrian activity, or other risk factors, which we know affect likelihood of collision. So you can think of blanket curtailment as 45-mile speed limits everywhere. It's not protective enough for a high-risk situation like a daycare parking lot, but it's too restrictive for a straight 4-line highway with no traffic. So speed limits work, but you need to know something about risk to set an appropriate limit. In the context of wind farm curtailment, acoustic data could provide that high-resolution information on risk that's been missing from the discussion. And we need to expand our toolbox for avoiding further impacts to federally listed species while focusing on species like the hoary bat that are particularly prone to impacts at wind projects. I am hopeful that our work will help demonstrate that acoustics may help meet the needs of wind companies and regulators alike in providing a quantitative foundation for rethinking our approach to curtailment. And with that, hopefully there's a little time for some questions.
Thanks so much, Trevor. We have time, just a couple minutes for questions. So let me read the first one. It is, does the acoustic activity differ when the turbine is off due to the sound of the turbine interfering with the ability of the equipment to detect bat calls?
We have not seen an effect like that. The turbines themselves don't seem to make a whole lot of noise in the ultrasonic frequency. So we have seen just as much bat activity recorded at turbines that are curtailed versus those that aren't. It's possible that wind itself could bias the amount of bat activity recorded just because of the way ultrasound moves through the air. But at the scale we've been analyzing, we've not seen that sort of an effect.
Okay, great, thank you. The next question is, Trevor, some researchers believe that because bats don't always echolocate when flying, acoustic monitoring may not reflect all of the conditions during which bats are at risk. We have not seen data that suggests absence of echolocating is a large factor, but have not specifically tested for this. Does your 80% correlation between activity and predicted fatalities tend to refute the theory that bats may not echolocate around turbines?
I wouldn't say so. Again, we're only sampling bat activity. We're not attempting to census every bat that flies through the rotor-swept zone. So if a certain proportion of hoary bats aren't echolocating, or alternatively don't happen to echolocate when they fly through the range of detection, I don't think that would bias our results unless there's a tendency for echolocation behavior to change with wind speed, for example. So obviously some of hoary bats, quite a few hoary bats are echolocating because they account for roughly 40% of the identified bat activity that we record at nacelle height. So a lot of hoary bats are echolocating, and I don't necessarily think it's a problem that we may not be recording all of them.
Okay, great, thanks. Unfortunately, we're out of time for questions right now. If we have more time at the end of the webinar, we'll come back and address more of those questions, and if not, then we can do them by email. So thank you, Trevor. And next we're going to turn to Katy Battle with American Wind Wildlife Institute. And let's see, Katy, can we hear you still?
Yeah, can you hear me?
Yep,
okay,
I can hear you. Great.
Okay, thanks, Paige. Well, yeah, hi, everybody. My name is Katy Battle. I am manager, along with Stu Webster, senior manager of AWWI's Technology Innovation Program, and I'm going to be presenting an overview of our smart curtailment project, the VBPS, or Vestas Bat Protection System. Okay, so the VBPS technology, Vestas Bat Protection System, is a software solution to the problem of blanket curtailment, which kind of Trevor was saying again, it's a coarse and uninformed strategy on how to manage the risk that wind turbines pose to bats and other wildlife. So the VBPS offers a smart curtailment solution to the blanket curtailment problem by integrating environmental and biological data to crunch through an algorithm that predicts bat fatality risk and issues curtailment orders in a more informed manner with the SCADA system at a wind turbine facility. And ultimately, this is going to offer wind turbine facilities improved efficiency, meaning less loss, unnecessary power production loss, and improved efficacy by reducing unnecessary harm to wildlife, in this case, bat fatalities. Okay, so our project's goal, again, is that we will develop and refine a smart curtailment strategy using the BBPS that not only reduces bat fatalities better than would blanket curtailment at a wind turbine facility, but also does this more efficiently by minimizing power production losses at the facility. So our project, we're going to be developing that smart curtailment strategy that the BBPS will execute with the SCADA system by developing and evaluating and refining a model that links bat fatalities with bat activity at a wind farm and models mathematically that activity in light of environmental variables at the wind farm, particularly weather data. So that's kind of the biological, ecological piece of this project. But again, smart curtailment is not just more informed ecologically, but it's also a better solution economically. So this project will be taking a look at the power production and the economic cost benefit of implementing this particular smart curtailment strategy against a more standard blanket curtailment strategy. Oops. So in our project, there's a few different major players. Of course, there's us, American Wind Wildlife Institute. We are the prime recipient. Stu is with me here today, and our Director of Research, Tabor Allison, is the principal investigator on this project. But we're also partnering with a couple different organizations. For example, Bat Conservation International, they are our field study people on this project. Mid-American Energy Company is the host site and also in charge of operations and the SCADA support that will be critical to deploying this project and conducting the experiment that will test out our VBPS smart curtailment strategy and analyze it for its economic impact. Vestas Americas is our vendor for the VBPS software, and Washington State University is the mathematical wizards behind the development of the model that relates bat fatality with bat activity and explains that activity in light of the weather data to inform the bat risk algorithm that VBPS will be processing to strategize when to curtail and when not to in a smart fashion. So the general approach to the experiment laid out in our project can be described in 3 phases. All of the boots on the ground work, or our field work, is going to be conducted at Mid-American's Orient Wind Farm in Adair County, Iowa. And the 3 phases that our project will go through, the first is the collection of the environmental, in our case in particular, weather data and biological data, that bat activity and bat fatality at the wind farm. Then those data will be cleaned, analyzed, and processed to develop a model that relates bat fatalities and activity with weather and creates an algorithm that VBPS will execute to predict bat fatality risk at the wind farm and issue a smart curtailment strategy in light of that predicted risk. And once we have that algorithm developed and loaded into the VBPS, the third and final phase of our project is the experimental testing. of VBPS. So we'll be launching that curtailment strategy at Mid-American's Orient Wind Farm and comparing and contrasting its efficacy and efficiency against both control turbines and turbines under blanket curtailment. So a little more detail on each of these three phases. The first, again, is the collection of environmental and biological data. So we'll be working with 10 turbines at Mid-American's Orient Wind Farm. And we'll be collecting weather data across various spatial and temporal scales at that wind farm, as well as a passive collection of SCADA data requests from the wind farm to get kind of background knowledge on curtailment and power production impacts before VBPS smart curtailment strategies are implemented. We'll also be collecting biological data on bat activity using acoustic detectors as well as thermal videography, and data on bat fatality informed by carcass searching at the turbines. Once we have all these data, that will help our project partners at Washington State University develop a model that best explains bat fatality according to the weather data. And then that best performing model will then inform the VBPS's algorithm on predicting bat fatality risk. Also, in the second phase, using the passive or background SCADA data that's collected in phase 1, Washington State will be developing a prediction on power losses that would result from blanket curtailment if it were to continue, and a predicted reduction in power loss once the VBPS's smart curtailment strategy is implemented. So those will kind of serve as the hypotheses and allow us to place our bets on how well we think VBPS will perform in contrast to blanket curtailment. And we'll test that in our third and final phase of the project, which is actually the experiment out at Mid-American. We'll be increasing our sampling pool from 10 to 18 turbines to allow for a randomized block design, with 6 turbines being complete control, no particular curtailment strategy of interest there, 6 executing on blanket curtailment, and 6 on the smart curtailment strategy as determined by the VBPS software. And again, during this experiment, we'll be collecting data similarly to that gathered in phase 1, so those data requests that will help inform the cost, benefit, and power production loss analyses that give the economic side of advantages that smart curtailment can offer, as well as the environmental data and biological data. So with this project, we're broken into a couple different budget periods with various outcomes. Our first budget period is really focused on getting through phase 1 and phase 2, as I just explained it. So we are aiming for a field study to begin this summer and go into the beginning of this fall. And then, of course, again, that collection of the phase 1 data will inform phase 2 development of the bat activity and bat fatality model to determine how to program, how to set up that VBPS algorithm for predicting bat fatality risk at the wind farm. And then once those phases are complete, we can move into the second budget period of our project that will be the experimental testing once VBPS is developed and launched onto a few turbines at Mid-American's Orient site. So if everything goes according to plan, we'll have 2 successful field seasons, a final report to the DOE on our project finding, and a manuscript to be submitted to a peer-reviewed journal for publication by summer of 2022. So that is, in a very small nutshell, our VBPS project. I did want to take a moment to thank the DOE for their support and funding of our project. And if you have any further questions about this smart curtailment project being led by AWWI or any of our other work out of our Technology Innovation Program, please don't be a stranger and contact either me or Stu. So with that, I think we'll have some time for questions.
Excellent. Thanks, Katie. So if anyone has questions, go ahead and type them in. We've already gotten several. The first question is, what cut-in speed will be assigned to the blanket curtailment group?
Hi, this is Stu Webster. And his dog. I wanted to respond to the questions for everyone. The blanket cut-in speed that we are currently contemplating is 5 meters per second, though the final decision on that will be made as part of the initial analysis of the site's sort of baseline conditions.
Great, thank you. The next question is, will your treatments rotate nightly between turbines during phase 3, or will they be fixed?
Currently, with the randomized block design, we are contemplating a duration of rotation 1 to 3 days, yet to be determined. And there is a possibility of needing to pivot from that, but as of right now, that is the current plan. And I should add that the sort of underlining assumption and objective of our study is to kind of work in close parallel with the other 2 studies taking place at the site, because we think one of the more premium opportunities we have with these 3 studies is the fact that they're being accomplished at the same time and in the same location, which is somewhat unprecedented. So very close coordination with the other 2 studies, so we could be influenced by some of their opportunities and constraints as well.
Great, thank you. Next question is, do you have future plans to test the approach at other sites with different weather regimes and a different suite of bats?
The motivation for this study is principally due to the original equipment manufacturer, Vestas, developing a patch, if you will, of their SCADA system. As a result of that, there's theoretically, at least, if not in practice, a lower hurdle to get over to implement and integrate a smart curtailment program, presumably other third-party equipment as well. So it provides us an opportunity to explore this perhaps a little bit easier with any Vestas-equipped facility with 2017 or newer platforms. So not in the plans, but certainly possible.
Thank you. Do you expect that the algorithm developed will be geographically or regionally specific or species specific?
The one challenge that we have with the project is that the host site is a new facility that was commissioned at the beginning of this year. However, there are a variety of proximate wind facilities near the facility, and we have quite a lot of data on not just species but also fatality rates. While they're variable and therefore leaving the host site somewhat unknown, we're using some fairly conservative assumptions about what numbers we should see there, but we do have, I think, a higher level of confidence about the species composition we're likely to see. What we're uncertain about is whether or not there will be sufficient power to do good analyses at a species level but we're fairly confident that we'll have sufficient power at the all bat species level. But regardless, we would be reporting out on data and findings at the species level, even if power wasn't sufficient to do proper analysis on those.
Okay, thank you. All right, we have 1 minute for one more question. How will annual energy production be presented? Raw dollars, percentage megawatts, percentage lost production, and given how loss generation numbers have been historically misinterpreted, how do you intend to put AEP in a way that can be meaningful to all stakeholders?
That's a great question. And the methodology for developing the AEP is a topic that remains outstanding. It involves some of the commercial sensitivities and proprietary information that different host sites will have about such data. However, what was immensely helpful is the DOE developed a draft guidance of what they're thinking in terms of a methodology that gives us a good base to start at. And again, depending on the host sites, there could be varying responses to how able we're to follow that method. But we'll work in collaboration with the DOE and the host sites to refine it. I think the one principal agreement across the board is that the studies, certainly at the Orient site, the 3 sites at the Orient site, should be consistent with the methodology used, so there is good comparability. Ideally, across at least all 4 of the smart curtailment projects, consistent methodology would be an ideal, but there is the variable of other host sites that need to chime in. So can't really speak other than that as to the exact output, but it is contemplated to be both dollars as well as production.
All right, well, thanks so much, Katy and Stu. And again, if we have time at the end, we'll circle back with some of these questions. But for now, we are going to move over to Crissy Sutter with Natural Power. Crissy, do we still have you on the phone?
Yes, I'm here. Can you hear me?
Great. You're coming through loud and clear.
Okay.
Yep.
Okay.
Thank you. All right, so you can take it away.
Okay. Hi, this is Crissy Sutter with Natural Power. So we are doing a 3-stage test, which I'll walk you through. And we have a bunch of good cooperators and partners for this project. So Natural Power is the prime, and then we have Alliant Energy, which is our host site. We have several independent engineering, SCADA, and other firms participating in these projects, as well as NREL. And then we have additional funding, not only the substantial funding from DOE, but additional funding from the Wind and Wildlife Research Fund. So in combination, I think we've got a good suite of participants for this project. And so just quickly, one of the reasons Natural Power chose the 3 tasks that I'm going to show you is because we have a background in doing providing services across the entire life cycle of the wind farm, both onshore and offshore. And so we have some internal skill sets that we thought were very valuable, and we wanted to leverage, particularly looking at some of the operational integration, SCADA, and other aspects of the smart curtailment system, as well as thinking about how we remove barriers. So we're hoping that by bringing some of these other skills into the team, that we will be able to address a lot of those barriers when you're thinking about putting third-party hardware and software on your wind farm. So as I mentioned, we've got a couple of goals and a couple of tasks. The first goal, like I mentioned, is to identify those barriers that prevent wind farms from using smart curtailment, and we know what many of those are. And so we've got a couple of tasks identified to help address those barriers. And then obviously looking at the efficacy, can we reduce both fatalities and increase AEP at the site? So we've got a couple of terms here at the beginning. And one of the important ones is what curtailment is. And so we're talking curtailment in this talk. We're talking about pitching the blades out to get the RPMs below around 2 or 3. The speed at which the turbine blades seem to be safe and that and turbines are no longer colliding. And for smart curtailment, we're talking about using real-time data. So both real-time weather data and real-time bat activity exposure data at the nacelle to decide when to curtail. Based on our modeling exercises, this results in a substantial increase in AEP as well as a substantial decrease in bat fatalities. So that is the approach used by this system. So we have 3 purposes: removing the barriers so that we can make it easier for wind farms to host third-party technology such as this, demonstrating the efficacy for all bats or maybe for some species or species groups depending on what the data looks like, and then reducing unnecessary curtailments and bringing back some of that lost AEP. So within this, there's 3 major tasks. Task 1 is around cybersecurity. So this is basically cyber infrastructure protection when you're thinking about integrating something new onto the grid like that. And we'll talk about that in more detail in a second. The next one is looking at SCADA integration and mechanical stressors at the National Wind Technology Center. And then the final one is that efficacy test. So the first task is cybersecurity. Any system such as a wind farm that is part of the grid in North America has to comply with various levels of cybersecurity readiness. And the higher the level you are, so for example, if you're a wind farm operator that also has nuclear facilities, you'll be at a level 12 within the NWCC compliance requirements. If you don't have nuclear facilities or you're a smaller megawatt, you'll be further down the list. But our intent is to ensure that our smart curtailment system is compliant up to level 12. So to do that, we have already written, well, we designed the system to have those protections in place from the beginning. We've written a document that describes that system and how we have created compliance with each of these readiness levels. The system and the document are being reviewed by experts at NREL to ensure that we have addressed all of those gaps and openings in which a bad actor might use an opening created by the BAT smart curtailment system to do something untoward, either to the turbine, the wind farm, or the entire grid. So we'll have that review, and any concerns they have about the system, we will then utilize that to modify the system, update the document, and iterate through a further round of reviews. And importantly, Alliant is our partner and is the host site for where we are doing our efficacy study in Task 3. And this report is part of their go, no-go decision-making process. So they will be determining if they're satisfied with our NWCC compliance. And if not, we will keep iterating. Hopefully, by the time we're through the NREL process, Alliant will be comfortable and will give us the opportunity to proceed with Task 3. Task 2 is the integration of the system on the GE turbine at the National Wind Technology Center. So this is already in place at this point. We did this about a month ago. So we are doing 2 main things for this task. One is looking at the SCADA integration and ensuring that our methodology for integrating into the SCADA is as painless as possible, as seamless as possible, and as universal as possible, so that this system could then easily not only be used on a given manufacturer of machines, but also any manufacturer of machines. So it could do GE, Vestas, Siemens, any of those things. And in addition, because this is a test turbine that we can manipulate at will, we are looking at mechanical impacts to the turbine of different curtailment regimes, primarily looking at things like load and other metrics to ensure that any activities related to smart curtailment are not creating issues about warranty or undue stress and strain and mechanical failure of wind turbines. Again, NREL will be writing a report on this, and that, again, will be shared with Alliant as part of their go, no-go decision making. And then finally, task 3 is the actual field study. So the system will be tested at the English Farms Wind Farm in Iowa. And we will be doing this in the summer of 2020 with a report out in July of 2021. And there are a few outstanding items in the study design still, but in general, this is where we stand right now. There's 69 turbines at the site. All of them will be enrolled in the study. They currently operate under a 6.9 meters per second technical assistance letter for Indiana bats. And we do have some post-construction mortality data from the site because they began operations last summer. So we do have some data to use both for the power analysis and for our planning purposes. So the current plan is, again, all 69 turbines enrolled. A portion of them will be full 160 by 160 meter plots. A portion of them will be just through roads and pads. There'll be 2 treatments, the smart curtailed treatment option and a second treatment to be determined. I think we've narrowed it down, but there's still some internal discussion going on, so we'll leave that there for now. The season will be August to October, and we've engaged a third-party contractor to do the post-construction mortality monitoring so that those doing the field study for the fatalities and those doing the other portions of the project are naive about what the other one is doing, so we can't inadvertently influence the post-construction mortality monitoring results. And so the last thing Jocelyn had asked us to address is commercial readiness. So this system is commercially ready at this point. We're hoping that by doing these 3 tests this year that we will be able to assuage some concerns and make it even more commercially viable. So at this point, we feel like the things that the DOE is funding and the other participants are funding or supporting will all make commercial readiness and viability that much stronger. So I think that is all I've got. That's the end for me. Paige, back to you.
All right, thanks so much, Crissy. Yeah, so if anyone has questions, go ahead and type them into the Q&A box. We do have a few minutes. The first question is U.S. Fish and Wildlife Service accepting the smart curtailment as avoidance, and how do you test under TAL, or is the operator assuming risk?
So this site will operate under a research permit issued by the Fish and Wildlife Service. So that will allow us to test this at a site potentially with endangered species present. So that's how we're addressing that issue. And then, as I said, there is ongoing discussion about exactly what the treatments are going to be. One will be a smart curtailment treatment, and one will be another treatment, and what exactly that treatment looks like as the control is still being negotiated with Fish and Wildlife Service and others.
Okay, great, thank you. The next question is, will you be comparing blanket 6.9 meters per second to acoustic activated up to 6.9 meters per second?
Again, the 2 treatment options aren't yet determined, so I can't tell you exactly what we are going to test at this site. That is still part of the ongoing discussion between all of the parties of the project.
All right, great, thank you. We have just a couple more minutes if anyone has any other questions. I'll just wait for a moment in case folks are typing. All right, the next question is, will your treatments be fixed or rotated between turbines?
The plan right now is that they will rotate between turbines.
All right, thanks. The next question is about the commercial readiness of the system. It's asking how is the system commercially ready if it hasn't been validated. You have yet to do any field studies on the effectiveness of the study.
So we have, we did some work actually in 2019 that's not published. So we do have some data. It's just not published at this point.
All right,
so
and then
yeah.
another, sorry, go ahead.
No, that's fine, go ahead.
All right. The next question is asking if you can please explain what a technical assistance letter is for those who are not aware of this.
Sure. So technical assistance letter is something the Fish and Wildlife Service has been issuing, I don't know, for 7, 8, 9 years now to wind farms that are within the range of typically the Indiana bat or another endangered species. And it says, I will crudely paraphrase, but it says that if you operate under the conditions specified in this letter, we will presume that there will be no take of this endangered species. And so it's, because sometimes it's a permanent condition and sometimes it is a stopgap measure that, that wind farms operate under until they get something more permanent like a habitat conservation plan and until take permit in place.
Okay, thanks so much for that explanation. We have time for one more question. If anyone else has a burning question, I'll give it just a second in case anyone is typing. And if not, we will move on to the final presentation today, which will be Christian Newman with the Electric Power Research Institute. Christian, can we still hear you? Are you on the phone or call?
I am on the phone. Can you hear me okay? Can you hear me okay?
Yes. Yes, thank you.
Okay.
You are coming through. All right, I will load up your PowerPoint here.
Good.
And as soon
Well,
as you see it, you can go ahead and get started.
Okay. So, well, first of all, thank you to NWCC and AWWI for hosting this. And also, again, I'll thank them at the end, but to DOE for funding this research. And I think one of the things that for people who don't understand that the cost of doing all of these studies that have been described is quite significant. And so it's imperative, I think, for the success and for broad understanding about these approaches, we really need this government funding. So thank you so much. If you're not familiar with EPRI, we're an independent nonprofit organization for the public interest of energy and environmental research. We conduct collaborative research projects for the benefit of the public in the United States and internationally. Most of our funding comes from a collaborative research membership model from regulated utilities. And in the U.S., 90% of the energy generated in the U.S. comes from an EPRI member or electric power utility. And then, although it's increasing, regulated utilities, which represent most of, our members, currently own about 15% of wind in the U.S. So, I want to talk a little bit about TIMR. So, TIMR is the Turbine Integrated Mortality Reduction Technology. Just like Crissy, their approach, it's a triggered approach. And I want to just I'm going to talk a little bit about the research that's already been done where we were able to sort of demonstrate some significant sort of effectiveness. And it also sort of left some unanswered questions. But I just kind of want to give a little summary of what has been done. So this idea has been thought about and worked on for the last 10 years by EPRI. And I want to acknowledge both John Goodrich-Mahoney, who used to work, who's retired now from EPRI, who was a champion of this, as well as Sue Schumacher from We Energies, who initiated this R&D within EPRI. So there were many other collaborators and funders to sort of get the project going. but they were two principal people that we definitely need to thank. So so essentially the TIMR was sort of developed over a period of time between 2012 and 2015 by Norman Doe Associates, and ultimately there was a field test in 2015, which lasted 77 days. And I'm pointing out a couple things just because I'm going to be sort of moving on and talking about what we're doing here, and there's some key differences. And in that initial study, essentially you were just comparing a triggered or a timer-controlled turbines versus controlled turbines, and so that was essentially the study. And also at that point in time, the treatment in terms of the timer was basically turning the turbines off when wind speeds were greater than 3.5 meters per second and less 0.8, and if there was a bat call on one of 4 rebat systems, which is essentially a bat recording system developed by Norman Doe. And we did daily searches on 80 by 80 meter plots, and they were done by humans. So the results were great, and in terms of the biological effectiveness. So over 80%, 84%, there was 80% lower fatalities from the timer versus control. And then we had enough little brown fatalities to generally characterize the effects for Myotis species, which again is one of those regulated species that Crissy was talking about. And we also looked and did some analysis about the loss of power, and for that study, the power loss was 3.2% annual generation, and we did some other analysis related to when the turbines were shut off versus 7 meters per second. One of the things that I want to sort of highlight is this is just one study that was done at one site. And for a long period of time, there's been a great need to try to replicate this study. And this is what DOE is, or replicate and validate what timer can do. And this is what we're working on. So I've highlighted a couple of the publications if people want to get into more detail about what was done previously. Oh, sorry, I just clicked off my screen. There we go, sorry. So what are we doing on this project? So what do we want to do? We want to essentially test timer over 2 calendar years. So we've done it in one year at one location. We want to extend the period of time the timer is being tested. So we focused at the last study on fall, and now we want to extend it into the summer. And then like all the other projects, we want to get into the operational and commercial costs of the timer system. Fundamentally, we're validating what was sort of done before and looking to sort of build off of the previous study. So I'm super excited that we have such an awesome team, and I want to highlight that this is very much a collaborative effort between all of these organizations. So for our study, USGS, they're leading the study design and the analysis, particularly around sort of the biological components. BCI, they're doing the field studies, leading the field studies, but they're also contributing to the design and the analysis. AWWI, they are invaluable in trying to coordinate between the teams, working with the host site in terms of being the liaison, and they're also supporting design and analysis. NREL also participating, doing design and analysis, and then EPRI, our renewables group, will be doing the power and economic analysis for the project. Norman Doe, they are the technology vendor. They've not been involved in the study design. They are just going out and installing and implementing the system, and the team will be evaluating how well it does. And then finally, I want to acknowledge Mid-American. They are hosting 3 projects, which is incredibly amazing, and their willingness to participate and work with all of us and support this research, we can't say enough for that. And so there are many other people within the organization that are working with us on this project. So the timer system. So what is the timer system? Again, it's a triggered system in that what we're going to do is we're going to put up 4 rebat systems. on 4 turbines within our study area. And so we have a target study area of 15 to 20,000 acres. The previous study, that was about the size of the wind farm that we did the study before, so we're trying to keep it essentially the same. Those 4 turbines will be recording bat activity and sending that data in real time to a timer server. And that timer server will be taking that, actually the raw calls come from the rebat systems, and then the timer server will be distinguishing bat from no bat calls for this project. And then that data will be integrated in from wind speed data and other data from the SCADA, which will be integrated in with a data logger. And then with that information, we'll be making determinations as to when to shut the turbines down for our study. And so now I'm going to talk a little bit about what we're going to be doing in terms of the overall plan. And I'll get to what the treatments are in just a second. So again, we're hosting the site at the Orient Wind Farm in Iowa. That the table there generally describes the habitat. It's agricultural, fairly uniform across the site. And so right now we are in the process of integrating and planning with Mid-American to install both the timer and the rebat system. In May, we are planning on installing the system at the Orient Wind Farm with the intent to test it to get ready for a June 15th start date, where we'll do the field testing and monitoring. And so in 2020, we're going to be monitoring for 126 nights between mid-June through mid-October. And then in 2021, we're going to be replicating this, but we'll be monitoring for 108 nights, again, starting approximately mid-June to mid-October. And then at the end of 2021, we'll be doing the data analysis, and in 2022, reports will be coming out, as well as manuscripts about the results. So getting into some of the details about the study design and some of the assumptions we made. So fundamental with any of these projects, we need to have high bat fatality. And so that was a criteria in terms of trying to select a host site. For this site, we do not currently have post-construction monitoring data at Orient, but Mid-American has been doing monitoring at many of the wind farms in the area, and so we have pretty good sense of what the range could be. We believe that the fatality, in terms of sort of building the study design and developing the power analysis, that we're assuming that there's going to be 15 bats per turbine fatality rates, and that's critical to our design. And we're hoping that there'll be lots more bats, again, which is a weird thing to say, a lot more dead bats, but that would be helpful in terms of the experiment. So we're going to have 3 experimental treatments. One will be a timer treatment, and so that in this study, unlike the other study, it'll be from 3.5 meters per second to an upper limit of 6.9, not 8. We're going to have a blanket curtailment treatment, which will be at 5 meters per second, and then control turbines that will operate normally. In order to get the power that we need for the study, we've determined that we need 18 turbines, and they will all be Vestas turbines. And there's a couple different types of turbines within sort of the wind farm, but the study turbines will all be Vestas V110. We're going to rotate between the 18 turbines every 3 nights. We're going to use a randomized block design, so on a nightly basis, 6 turbines will have the timer treatment, 6 turbines will have the 5.0 meter treatment, and then there'll be 6 turbines with the control treatment. And so this allows the treatments to be balanced among the turbines each night and within turbines every 18 days. In year 1, we are going with 160 by 160 meter plots. Again, going from the first study where we did 80 by 80, we're going much bigger. And the reason why is because in the last couple of years, there's been a number of studies that indicate that bats may be falling further from turbines than we thought. But for our study, we want to make sure that we're essentially capturing as many of the dead bats as possible. And so we're going out to a larger plot area. In year 2, At the end of year one, we're going to do analysis, and if we determine that there are enough bats sort of falling within 140 by 140 meters, we'll downsize to 140 meter plots. We're going to be doing daily searches. Again, a primary difference for our study between this and the last time is we're going to use dogs. And for many people who are probably on the phone, but some people may not know this, the dogs have a much higher search efficiency in that it's much easier and they do a much better finding the dead bats than people. And so we've tried to design this to have the greatest chance to pull out sort of the statistical differences between each one of these treatments. At the end of year one, we will again be doing analysis, and depending on a number of factors, primarily if there are lots, much higher sort of bat fatality than what we assumed, we might be able to drop down and use humans in the second year. So we're really excited about this project. We think it's gonna result some really good results and be able to try to sort of address some of the questions that occurred on that first study. So I want to highlight that this is a collaborative effort between many, many organizations, and I want to thank them all for getting us to this point. And I also want to thank DOE for their funding, and I also want to thank the other presenters today. You guys laid a lot of great foundation for me, and I'm really excited that broadly that this research is being funded to try to better understand smart curtailment. So thank you so much.
Great. Thanks so much, Christian. So we have a few questions that have come in, and we do have a few minutes for questions on this presentation. So if anyone has a question, please go ahead and type it into the Q&A box. The first question is noting that in the AWWI presentation, they mentioned that the study site is also the Orient Wind Farm, and this question is asking, is there any concern for confounding effects if more than one study is occurring at the same site?
Good question. We've talked about that and gotten our statistical people, the really smart people who is not me, together to talk about this. We do not believe it's going to be a confounding effect, and we are going to be working to try to make sure that as the turbines are picked out for each one of the studies, that it doesn't create additional sort of knock-on effects in terms of future analysis.
All right, great. The next question is referring to an earlier slide where you mentioned the overall bat fatality rate, and the figure presented was 15 bats per turbine. Is that per year?
That is a good question. That's actually that's within the period of time that we're sort of doing the study. So yeah, I mean so it's actually not per year, but that's within the period of time that we run the experience. That's the assumption that we're going on, and that's based off of some fatality data from the surrounding region, and we believe that we'll be able to get that amount during our study.
All right, great. The next question is, will you also be comparing power loss between blanket curtailment and the TIMR test group?
Yes. So we will be comparing power loss between each one of these treatments, and Stu alluded, or not alluded, but he discussed that there's also some ongoing discussions between all the awardees and DOE and NREL to come up with a common approach. So, but the answer to that question is yes.
All right, great. We have a few more minutes for questions on this presentation, and I'll give it a second if folks are typing or thinking of their questions. And if we don't have any more questions from participants for Christian, we did have a number for Trevor, and maybe we can get to a few of those before we wrap up. Trevor, are you still on the line?
Yes, I am.
Okay, great. So I think, well, I'll say once again, thank you, Christian. If anyone else has a question for Christian, go ahead and type it in and we'll come back to it. But with our few minutes remaining, let's address a few of these questions for Trevor. So Trevor, I'm just going to dive in here. Could you please repeat or specify how fatality data were collected?
In the previous projects, fatality data were collected according to a standardized fatality monitoring protocol. So it differed between sites. At one site, it was a 3-day interval, human search, within turbine clearings. At the other site, it was weekly. So these were the standard monitoring programs that were negotiated for each site with the state agencies. So it's different from, notably we're proposing to do a different type of fatality monitoring than the AWWI and EPRI studies, which are relying more on fatality monitoring for some of their data. Our purpose, our approach is to use what I call compliance level fatality monitoring that's being done at our host sites to fulfill their permitting requirements and so forth. And the primary objective of those strategies is to generate an empirical fatality estimate, not necessarily to get the highly temporally precise, at least daily searches. So we're taking advantage of monitoring that's already taking place, and similarly, that's what we did at the previous sites.
Great, thank you. And the next question is, in the graphs you were showing of acoustic activity versus fatalities, was the activity measured during pre-construction or post-construction?
I can go back. So those graphs were measured simultaneous to the fatality data. So in other words, they were measured on the tops of turbine nacelles during the same monitoring period in which the fatality data were collected. So, for example, this red dot represents a fatality estimate associated with uncurtailed turbines, and on the vertical scale, and the horizontal scale is the activity level that was exposed to turbine operation at those same turbines during the same interval.
Okay, great, thank you. The next question is, what weather parameters are being evaluated? Just wind speed and temperature, or time of night, precipitation, barometric pressure, etc.? And the second part of the question is, have you seen one parameter being more important than another, more important meaning having a more significant effect on that activity?
Right. That's a great question. We are primarily focused on temperature and wind speed. The reason being these metrics are already measured at virtually every commercially installed commercial turbine. So my thinking is that the strategy is focusing on parameters that explain the greatest amount of variation in activity first, and then winnowing down to more to subtle factors. So I've actually seen temperature and wind speed to explain similar amounts of variation in bat activity. Notably, however, seasonal patterns in bat activity can explain as much or more. So most attempts to model bat activity have found that time of year, temperature, and wind speed are among the most influential factors. We are not at this point planning to evaluate other factors such as wind direction, barometric pressure, humidity, not because they don't affect bat activity, but because they affect bat activity to a lesser degree than these other variables, and or they're not typically recorded and available to SCADA systems without some substantial modification to the existing hardware.
All right, thank you. And we are just about out of time, so there's still a handful of questions we didn't get to. What I will do is send those questions around to the presenters. I think we have a few more for you, Trevor, and a few for Katy and Sue. We'll get those questions answered by email, and then we'll send them out to everyone who was registered for this webinar so everybody can see the answers. So with that, I think we are going to wrap up. We're right at the end of our time here. I want to thank our presenters again for taking the time to share their projects with us. It's really interesting to see these studies, and we look forward to seeing the results. Thank you to DOE, Jocelyn for joining, and to NREL for all of your support on making sure we can get the word out about all of this research. And as a final reminder, we will be putting the recording and PowerPoints up on the NWCC website within a few days. The recordings and PowerPoints for the previous webinars in this series that Jocelyn mentioned, we had one on deterrent, bat deterrent and monitoring technologies last week, and in January we had one on offshore monitoring systems. So if you're interested in that, please go to www.nationalwind.org. And thanks everyone for joining. Have a great afternoon, everybody. Goodbye.